The astrophysicists' recent discussion of the interstellar object known as 3I/Atlas has sparked intense scientific debate, primarily because of the surprising and complex behavior the object displayed as it journeyed through our solar system. In a detailed Medium post, he laid out a rigorous and deeply analytical explanation for why he believes the object underwent fragmentation. His argument was built upon newly released images from British astronomers Michael Buechner and Frank Niebling. These images, captured with high-precision equipment, reveal that Atlas developed two enormous features: a massive anti-tail stretching toward the sun, and a separate, elongated, smoking trail extending in the opposite direction. These trails resemble powerful jets, but on a scale far beyond typical cometary behavior. According to Loeb, the dimensions of these jets are staggering, one reaching roughly 620,000 miles in the direction of the sun, and the other stretching about 1,860,000 miles away from it. Distances of this magnitude imply that the object was shedding a colossal amount of mass, likely due to extreme heating and subsequent sublimation as it approached the sun's fierce radiation. Loeb emphasized that for a natural comet, the outflow velocity of such jets should follow well-understood physical expectations. At the distance of 3I/Atlas from the sun, the jets should have been flowing outward at an expected velocity of approximately 248 miles per second. Based on this speed, Loeb calculated that these streams of material would have to persist for 1 to 3 months in order to form trails as enormous as those observed. For such endurance and magnitude, the comet would need to undergo a significant transformation, one far more dramatic than anything typically seen in ordinary comets. This is where Loeb's analysis began to question whether Atlas could truly be a conventional natural object. Sublimation, the process by which a solid turns directly into gas, is a common mechanism in comets composed largely of ices. However, for the amount of carbon dioxide ice and water ice required to produce jets of this magnitude, the interstellar object would need to absorb an extraordinary amount of solar energy. Loeb meticulously examined Atlas' perihelion distance, the point at which the object was closest to the sun, and calculated the absorbing surface area necessary to produce the observed mass loss. He determined that the absorbing area would need to be roughly 617 square miles, equivalent to a sphere about 14.3 miles across. This estimate stands in stark contrast to earlier size projections derived from Hubble telescope data, which suggested the nucleus was only around 3.1 miles in diameter and had a total mass of about 33 billion tons. The discrepancy is not small. It implies a vast difference in the physical structure and behavior of the object. In interviews, including his comments to the New York Post, Loeb highlighted this inconsistency. He said that if Atlas were a natural comet, its original structure would not align with the required surface area unless it had broken apart into many pieces. Such fragmentation would significantly increase its total surface area exposed to sunlight, thus allowing it to sublimate at a much higher rate. Loeb estimated that the comet would need to break into tens of fragments in order for the theoretical models to match the observational data. He compared this violent transformation to the burst of fireworks, triggered by overwhelming heating from the sun's radiation, causing the object to explode into several distinct pieces. This process, he explained, would naturally produce the large anti-tail and extended trail observed by astronomers, because fragmented surfaces would expose fresh ices to extreme temperatures, making sublimation occur more vigorously. While the fragmentation theory seems convincing to many scientists, Loeb has also pointed out other clues that hint toward Atlas cometary identity. On October 24th, the Meerkat radio telescope in South Africa achieved a remarkable milestone by detecting the first-ever radio signal from 3I/Atlas. Although earlier attempts in September yielded no results, the October observation provided something significant: the detection of radio absorption lines from hydroxyl radicals. Hydroxyl radicals often appear when the sun's ultraviolet light breaks apart water molecules. Their detection strongly suggests that Atlas contains water ice, a key component of natural comets, and that it was losing water due to the sun's heat during its flyby. The instrument's measurements aligned well with models of cometary dissociation, and several researchers interpreted the data as further confirmation that Atlas was undergoing natural mass loss rather than exhibiting artificial behavior. From this perspective, the presence of hydroxyl radicals appears to weaken the idea that Atlas might be a technological object sent by an extraterrestrial civilization. Loeb himself has previously suggested that unusual interstellar visitors could potentially be alien probes designed for reconnaissance, a hypothesis he explored particularly when discussing the earlier visitor 1I/Oumuamua. However, even though the new data supports the natural comet explanation, Loeb has made it clear that these findings do not entirely invalidate the possibility of extraterrestrial origin. His reasoning centers on whether Atlas remained structurally intact during its closest approach to the Sun. If future observations indicate that the object did not fragment as much as expected, or survived in a way that defies the physical limits of known cometary materials, then such resilience could point toward an artificial or engineered structure. In Loeb's view, the question remains open because the object's unusual behavior complicates traditional understanding. Natural comets are expected to be fragile. When confronted with intense solar radiation, they typically fracture or dissolve entirely. If Atlas defies this expectation by keeping a coherent structure despite massive jets and solar heating, it would leave open the possibility that the object is composed of unknown material or is reinforced in an unnatural way. Loeb argues that this is precisely why interstellar objects warrant careful examination. They come from beyond our solar system and may represent types of phenomena or technologies that humanity has never encountered. As observations continue, scientists worldwide remain focused on learning more about interstellar debris, especially objects such as 3I/Atlas that do not fit neatly into established categories. Researchers hope to gather data on its trajectory, rotation, mass, and chemical composition. Ground-based telescopes, radio observatories, and even future space missions may provide additional clues about Atlas' true nature. If the object behaves consistently with known cometary physics, showing signs of progressive decay, splitting, or evaporation, it will further strengthen the case for a natural origin. If not, the scientific community may be pushed to consider alternative explanations, including the possibility of alien technology. The debate surrounding Atlas reflects a broader shift in astrophysics, one that embraces open-minded investigation of the unknown. Loeb has often emphasized that dismissing unconventional possibilities without evidence is unscientific. Instead, he argues for rigorous testing, careful measurement, and unbiased examination. For him, the key question is not whether the alien hypothesis is bizarre, but whether the data can rule it out or keep it alive as a valid possibility. For now, considering the massive anti-tail, the extended smoking trail, the energy calculations, the detection of hydroxyl radicals, and the potential inconsistencies in the object's fragmentation, Atlas remains an intriguing mystery, one that challenges assumptions and invites deeper study of what might be traveling through interstellar space.